Hello and welcome to my channel. You probably remember my last video. There I showed which programs put the most strain on the CPU, what the temperature is, how fast the fan rotates, and how much energy is used. Check out the video if you haven't seen it yet. I was wondering if I can program code that uses less power and if I can write an own stress test that uses even more power. In my first program, I wrote a simple counting loop that counts down. It should start over again, so I always set the value back to 100. This could happen, for example, in a game in which life points are reduced with every hit. I've written this program 3 times. Once with the data type character, once with integer, and once with long. A character is only 1 byte long, integer is 4 bytes long, and long is 8 bytes long on this operating system. The variables can therefore remember numbers of different sizes, but in this case the numbers are so small that it fits in all cases, and exactly the same thing happens. By the way, the assembler code of this program looks like this. In the first line in particular, you can see that the data types have different width. The general flow of the program is the same in all 3 cases. I was too lazy to write a real multi-threaded application, so I just run the program 4 times. This means that the CPU is fully loaded, and differences are hopefully more noticeable. You can see how busy it is in the top line. On the right side, in the left small icon, which contains the C, the workload is given in %. The result is surprising. The power consumption of my simple program is a little higher than sysbench. The temperatures look the same. But you can see from the fan speed that my program uses little more energy. I will go into this more detailed later. I was a little disappointed that I basically couldn't see any difference between characters, integers and long. So does the width of the data have no impact on energy consumption at all? How can I further increase power consumption? To do this, you need to know something about how the CPU works. When an assembler instruction is called, then that instruction must be first fetched, decoded, executed, memory is accessed, and the result is written back. The next command then does the same. The instruction is fetched, decoded, executed, memory is accessed, and the result is written back. If the commands are depending on each other, then they always have to be done one after the other. With pipelining, on the other hand, these steps are sometimes carried out in parallel. While the first command is still decoding, the second command is always being fetched. Of course, this trick only works if the second command doesn't need the result of the first command. The execution of programs can be significantly accelerated by pipelining. Here you can see the new source code. I added 2 integers that are independent from each other. So I hope pipelining will execute them nearly in parallel. Of course, I did it all though with characters and with long. So I start my new program 4 times again and observe the measured values. In the top line you can see 3 fields on the right. On the left you can see the CPU load, in the middle the temperature, and on the right the GPU load. In the lower window the temperature is measured again. The frequency and the speed of the fan are displayed. The speed of the CPU in today's tests is always the full 2.4 GHz. When idle, the frequency is only 1.5 GHz. You can see the results in this table. Temperature and fan speed don't seem to make any differences. When it comes to energy consumption, you can now clearly see that character, integer and long consumes different amounts of energy. So if you use a smaller data type, you can actually save energy. A large data type consumes more energy. I still don't call the CPU as much as /ng. I will think about how I can make it more energy hungry later. The small differences in temperature and ventilation are surprising. You can only see how this happens once you look at how such a measurement was carried out. My pi measures the temperature 3 times in total. Once for the display in the top right corner, once for the display at the bottom of the terminal, and once not visible for the fan control. Since these measurements do not take place exactly at the same time, the values are slightly different. If the fan control program of the Raspbian OS measures a value below 50 degrees Celsius, then the fan stops. Above 50 degrees Celsius, the value is increased to 30%. Above 60 degrees Celsius, it rises to 50%. And above 67.5 degrees Celsius, it rises to 70%. Only if the temperature is above 75 degrees Celsius, the value is set to 100%. The fan remains at the increased speed until it falls below a certain other temperature. So in this case, we can see that around 67.5 degrees Celsius, the speed of the fan increases from around 3000 rounds per minute to almost 5000 rounds per minute. It remains this speed until the temperature has fallen clearly again. The difference in the previous table is not the maximum values of the temperature or fan speed, but rather how long the fan rotates at higher speed. Next, I wanted to know whether the computer is slower at characters, integers or long. The clock speed was always 2.4 GHz. I put my code in a loop and made sure that this time the program didn't run endlessly. The outer loop counter is constant long in all 3 programs. However, I tried the bold data type with character, integer and long again, of course. I then measured how long it took to run the program. Since the measurements vary relatively widely, I carried them out several times and wrote down the median value. As expected, the values were approximately the same. Long seems to be a little bit slower. Unfortunately, I can't explain why this is the case. But it looks like we don't have to worry about slowing down a program by using larger data types. To improve my stress test some more, a CPU not only has an arithmetic logic unit, but also a floating point unit. My idea is not only use integers of type long to achieve the highest possible energy consumption, but also use floating point numbers of data type double. These are also 64 bits long. Presumably, the CPU can run the arithmetic logic unit and the floating point unit almost simultaneously. I improved my source, not only using data type long for integers, but also the data type double for the floating point numbers. Otherwise, my program is more or less unchanged. The calculations are again independent from each other, so pipelining should still work fine. My new program reaches a maximum temperature of 76 degrees Celsius. And the fan rotates at over 8000 rounds per minute. The energy consumption is 10.7 watts. I even beat FAT with this. By the way, I carried out today's measurements at a room temperature of just around 17 degrees Celsius. Let's take a look at the program execution of my stress test. We will see that the temperature rises over 75 degrees Celsius. The fan spins at 8000 rounds per minute. This is sadly loud. The fan maintains its speed until the temperature has dropped clearly. The fan then only rotates at around 5000 rounds per minute. It only accelerates again when the temperature is above 75 degrees Celsius again. Of course, my stress test is not yet optimal. There are certainly still many opportunities to improve it. Other operators may use more energy. The if statement may only use a small amount of power, so it might be removed and/or replaced by a goto statement. I haven't put any strain on the GPU yet, and the program should perhaps be written to automatically use multiple threads. I invite you to improve my source code. I will put a link in the video description. You should use an energy meter as it makes it much quicker and easier to measure improvements to the program. It is important to me that you have to be careful when watching cooler tests. Some people measure the temperature far too rarely, and then it depends on chance whether the measurement was carried out at the moment when the CPU has reached 75 degrees Celsius, for example, or at the moment when the CPU was perhaps only 70 degrees Celsius hot. When testing a cooler, you not only have to measure over a longer period of time, but above all, you have to measure very regularly and observe how the temperature goes up and down and what the fan is doing. The measurements of the maximum temperature are also not very meaningful, as we do not know how long they stayed. Was the maximum temperature only for a few seconds or almost the entire time? That's it for today. Happy holidays!